All right. All right, guys. Again, as I said, the wire experiences a force because the magnetic field in the current interacts with the magnetic field of the magnet, and this results in a force. Now, the next step, we need to learn how can we find the direction of that force. The direction of the force is given by Fleming's left hand rule. All right, in Fleming's left hand rule, remember we talked about Fleming's right hand rule, but in Fleming's left hand rule, we put our fingers in this same arrangement, like in right angles. If you remember, we talked about the right hand rule before, and this time we're going to talk about the left hand rule. The left hand rule is used to find the direction of the force acting on the wire. The direction of the force acting on the wire is given by Fleming's left hand rule, where the thumb is the force, the index is the field, the second finger is the current. Force, field, current. Okay? Now, what I always do is that I arrange my hand in the direction of the field. That's the field, that's the current, the force is up. In that case, the force is upwards, so the wire is going to jerk up. All right, in this case, the wire is going to move up. If we reversed the battery, now this is the positive, the small one is the negative, so the arrow moves like that. Again, field, but this time the current is going in this direction and the force is going, my thumb is going down. All right, like that. Field, current, force. So the force goes down. Reversing the direction of the current reverses the direction of the force. Okay, I'm going to explain it in a more clear manner, okay, so that you understand how to use Fleming's left hand rule clearly. If I have, this is my field, south, so the field is in this direction. Current, I'm gonna say current is into the paper or into the board. Now I need to know the direction of the force. I'm going to start with a field. Now this points in the field. My second finger points in the direction of the current. So I'm going to start by pointing my first finger in the direction of the field. My second finger in the direction of the current. My thumb points down. So my force is, the wire will move down. If north, south, but this time the current is out of the page. Okay, let me erase the field because for now we know that the field goes from north to south. Again, field, now the current is going to go up like that. The force will be upwards. All right. Again, field, current, force. Okay, this is how you use Fleming's left hand rule. If I have two wires. I'm going to say, again, I'm going to flip the magnetic field this time. North. And I have a wire here and a wire here. Okay, two wires. One of them is current is flowing into the board. The second one, current is flowing out of. Here, current is flowing into. Here, current is flowing out of the board. I need to know the direction of the forces. And the field is in this direction, north to south. How can I know the direction of the forces? Again, by using Fleming's left-hand rule, but this time the field is going to go like that, current down. Okay, let me just try to go up a little. Field is in this direction, current is down, force is up. So here the force is up, and here the force will go down because the current is reversed. Alright? This arrangement is very similar. If you want to draw this in 3D, it's very similar to a solenoid or a coil. This is the south, and this is the north, and I have a coiled up wire like this. Comes back here. The current here is going in this direction, here is going in that direction. It means that this is the positive and this is the negative. So over here, coil will go up. Over here, coil will go down. This will create a turning effect. So the coil is going to rotate from its current position into a vertical position. It will just rotate. If it was like that, it will rotate, because part of it is going up and part of it is going down. So the coil is going to rotate. Why is part of it going up and the other part is going down? Because here the current is going into the board, here the current is going out of the board, and if we reverse the direction of the current, the force reverses. So here a turning effect takes place. Alright? Again, why is the coil moving? Because there is a current, and the current has a magnetic field. The magnetic field of the current interacts with the magnetic field of the magnet, causing this force. If there were no magnets present, no force will take place. So for all of this to take place, we need to have a permanent magnet to supply the main magnetic field. All right? Okay. Now it's time for your questions. Okay, Sama, you have any questions? Malak, any questions?
I don't have any questions, but I feel like because then I couldn't really hear a couple of things, so I'll just watch the recording again later, and then if I have any extra questions, I'll ask you. But what I heard, I understood.
Okay, Lena, any questions?
No.
All right, Thuraya, do you have any questions?
No.
All right, Nujud, any questions about the force? Hassan, any questions? Dana, Any questions? Okay. Now, let's put this, what we just understood, into context. So these are the notes that you need to take, and I would advise you to take pictures. So to increase the size of the force, we increase the current, because more current means more magnetic field due to the current, more force. Increase the number of individual wires. So instead of using one wire, you can use a coil, or you can increase the length of the wire in the magnetic field. Increase the strength of the magnetic field, which means that use a stronger magnet. So your permanent magnet, if it's a strong magnet, the force will eventually increase because more interaction between the two magnetic fields. Increase the length of the wire within the magnetic field, which can be done by increasing the number of turns of the wire. Cool? So all of these are factors that are used to increase the size of the force. Note all of these. They're very important. They're linked to things that we're going to study next. Then we go to Fleming's left-hand rule. In Fleming's left-hand rule, it's used to find the direction of the force. Fleming's left-hand rule is used to find the direction of the force acting on the wires. Okay? All right. If I have a magnetic field drawn by these x's, okay? X's means the magnetic field is into the page, and I have a wire, and the current is flowing in this direction. In which direction, or what will the direction of the force be? If you have an answer, raise your hand. I have the field, I have the current, I need the direction of the force, and the direction of the force is found by using Fleming's left-hand rule. So, what is the direction of the force? Yes, Lena.
Upwards.
Upwards. Okay, let's see how Lena came up with that answer. Again, Fleming's left-hand rule. It's like that. Field is into the page. Current is in this direction. My thumb is gonna point upwards. So the direction of the force is going to be upwards. This is the direction of the force. This rule is directly related to what we talked about in atomic physics, which is deflection of alpha particles. Okay? If we want to know the direction of deflection of alpha particles, it's actually the same if the field is into the page and alpha particles are moving in this direction, okay? They're going to be deflected upwards because alpha particles takes the same direction of current flow. But beta particles, on the other hand, deflect in the opposite direction, and the deflection of beta particles is more than the deflection of alpha particles because beta particles are lighter. Okay? So Fleming's left-hand rule is used to find the deflection of alpha particles and beta particles in a magnetic field. So if you know how to use Fleming's left-hand rule, you can use it to find the directions of deflections of alpha particles and beta particles. All right? If you just know the direction of deflection of alpha, you can directly know the direction of deflection of beta, because it's just the opposite direction and it deflects more than the alpha particles. Does that make sense, guys? Good? All right. After that, knowing Fleming's left-hand rule, first finger is field, second finger is current, third finger or thumb is movement of the force. All right, so this is current, field, force will be down. Try to use Fleming's left-hand rule to double check the direction of the force, because before moving forward, you need to know how to use Fleming's left-hand rule. If you want me to give you more examples about Fleming's left-hand rule, please let me know. Okay. All right. I'm going to ask Malak. All right, Malak. Can you hear me?
Yes, can you hear me?
Yes, I can. Can you show me the direction of the deflection of the wire in the drawing here?
Right.
Come again?
Right.
The direction of deflection is either out of the board or into the board. Which one is it gonna be?
Wait, 1 second. Out of the board.
Out of the board. Okay, let's see. We're gonna start again with field. Okay? With field, I'm going to just change the orientation like that, so that it's just easier for me. I don't want to stand that. Field, north to south. Is that clear, Malak?
Yes, it's clear.
Is my second finger pointing in the same direction as the current?
No.
So I need to reverse it, correct? Where is my thumb pointing now?
Into the board.
Into the board. So the direction of deflection is into
the board.
The board. All right? Into the board, and
Thank
this
you.
is how Fleming's left-hand rule is used. All right? Okay. Moving on. Forces on charged particles, we just talked about it, alphas and betas. If you have any questions, let me know. And then we have questions. All right. A current carrying wire is perpendicular to a magnetic field and moves up. If the current is reversed, in which direction will the wire move? In which direction will, please raise your hands if you have an answer. No hands, no answer. Again, if the wire already moves up, if the current is reversed, in which direction will the wire move? Yes, Nujud.
Down.
Down. It's in the opposite direction. Good. Okay. A current carrying wire is parallel to a magnetic field and does not move. If the current is reversed, in which direction will the wire move? Okay. Lena?
Number 3.
No movement. Sama, do you agree?
Yes.
Yes. No movement, because if the wire is parallel to the magnetic field, there is no movement. The wire needs to be perpendicular to the magnetic field for the two magnetic fields to interact. If the wire is parallel to the magnetic field, there will be no interaction between the fields and there would be no force. If you realize that the wire is always perpendicular to the field, it's a 90 degrees between the wire and the field. All right? So if the wire is parallel to the field, there would be no movement, there would be no force between the wire and the magnet. Good one, good one. Okay. Study the figure below. What is the direction of the force on the wire? Okay, what is the direction of the force on the wire? You have 1, 2, 3, 4. If you're ready with your answer, raise your hand. Come on. What is the direction of the force? Okay, I'm going to... Okay, Nujud. Nujud.
I take 1.
Down. Okay. Sama.
I thought it was right.
Right. Malak.
Down.
Down. Lena.
Out of page.
Out of page. Okay, first of all, remember that the direction of motion is going to be, it cannot be right, or it does not get attracted to the South Pole or the North Pole. All right, it moves perpendicular to the South Pole and North Pole. All right. Now, Lena said out of page, Malak said, I think, down, and I think Najud said down as well. Sama said, right? Now, let's see.
Wait, no, sir, I changed my mind. It's number 2.
It's out of page as well. All right.
Yeah.
Okay, I'm just going to make a very simple drawing here. North and south. And I'm going to demonstrate again Fleming's left-hand rule. All right, you start with You start with your index finger, and the index finger is going to point from north to south. Okay, so it's like that, north to south. My second finger is in the same direction as the current. And look at my thumb points towards the camera here. It means that my thumb points out of the page. All right, so the answer for this question is 2 out of page. But before we proceed, let's see if the answer, the answer is correct. Before going to the next question, Sama, what did you do and why did you get it wrong?
I didn't put my middle finger down.
Okay, now are you getting it now? Is it getting easier each time we have an example? Are you getting it?
Yeah, I'm getting it.
All right. Okay, moving on to the next question. It says also study. Hold on. Study the figure below. What is the direction of the force on the wire? All right, you have the current direction, you have the field direction, and you have options 1, 2, 3, and 4. When you're ready, raise your hand. Come on, Threya, Hassan, more interaction, please. All right. Okay, Sama, what's your answer?
Up.
Up, Sama. Yes, Sama, you're getting it now. But wait, let's make sure it's the right answer. And the answer is correct, Sama. Good job, Sama. Keep it up. Keep up the good work. Okay. So this is Fleming's left-hand rule, and this is Lorentz force. Force on a current carrying conductor. Now we know that if we reverse the current, it reverses the force. If we reverse the magnetic field, it reverses the force. If we increase the strength of the field, it increases the force, and so on. Before going to DC motors, do you have any questions about what we just took? Any questions, guys? If everything is clear, please type in clear so that we move on. Okay. Okay, Malak, Lina, Najud. All right. All right, so let's keep going. DC motors. Now, this is a DC motor. That's a small illustration of a DC motor. It rotates and rotates. And it's one of the most important inventions. All right, it uses the same idea of force on a current carrying conductor. We see DC motors in our everyday life, in fans, in what else? In water pumps, in electric drills. Where else do we see DC motors? A DC motor changes electrical energy into mechanical energy. It gives the rotation force. It causes a torque. So, how does it work out? Okay. So again, if we remember these factors of increasing the force, increasing the strength of the magnet, that's the things that I talked about right now. Okay, explaining how a DC motor works. Right, I'm just going to explain it with a quick video, and after that we're going to discuss the video. Okay, then we'll discuss the video together. It's a 4 minutes video, but it's worth the time.
In many portable home appliances, automobiles, and types of industrial equipment. In this video, we will logically understand the operation and construction of a commercial DC motor. Let's first start with the simplest DC motor possible. It looks like this. The stator provides a constant magnetic field, and the armature, which is the rotating part, is a simple coil. The armature is connected to a DC power source through a pair of commutator rings. When the current flows through the coil, an electromagnetic force is induced on it according to the Lorentz law, so the coil will start to rotate. You will notice that as the coil rotates, the commutator rings connect with the power source of opposite polarity. As a result, on the left side of the coil, the electricity will always flow away, and on the right side, electricity will always flow towards. This ensures that the torque action is also in the same direction throughout the motion, so the coil will continue rotating. But if you observe the torque action on the coil closely, you will notice that when the coil is nearly perpendicular to the magnetic flux, the torque action nears zero. As a result, there will be irregular motion of the rotor if you run such a DC motor. Here is the trick to overcoming this problem.
Alright guys, for starters, we talked about in the video, the person mentioned the rotor and the stator. Okay, these are terminologies that are not in the syllabus. We just talk about a permanent magnet that supplies the magnetic field and the coil that rotates. Now the question is, why does the coil rotate? Okay, the coil rotates again because current is flowing in different directions. Okay, in a part of the coil the current is flowing towards, and in the other part the current is flowing in the opposite direction. So again, let's just take it slowly here, and I want you to just follow the arrows by using Fleming's left hand rule. Alright, use Fleming's left hand rule to show the direction of the force. Alright, now use Fleming's left hand rule to make sure that in this part its force is going to go up, and in the other part the force is going to go down. Alright, it keeps rotating.
The torque action is also in the same direction.
Alright, so if the current is flowing in this direction, the motion is upwards. If the current is flowing in the opposite direction, the motion is downwards. Alright, now if I want to show this in an end view, if this is the north and this is the south pole, and here the current is flowing outwards and here the current is flowing inwards. So again, I'm going to use Fleming's left hand rule. Okay, if the current is flowing inwards, the force is down. If the current is flowing outwards, the force is up. So here the force is down and here the force is up. When the forces act in such a direction, I'm going to say that the direction of motion is anti-clockwise. Okay, it rotates anti-clockwise. That's the first thing that I need to know. All right, so it's like that as I drew it last time. Okay, and north, south, and this is my coil, but it's connected to commutator rings. All right, these commutator rings, there's carbon brushes here. The carbon brushes ensures conductivity, and from the carbon brushes there are split ring commutator rings. All right, they're like semicircles. All right, not full circles, they're semicircles like that, and another semicircle here on the other side. They're not connected to each other. They rotate with the coil, and out of the commutator rings then it goes to a battery or a power supply. All right, let me just go up a little. Now there is a certain function of commutator rings. Let me show a better drawing, which is here. Okay, these are the commutator rings. They're called the split ring commutators, and these are the carbon brushes, and this is an end view of the electric DC motor. Now, what does the commutator rings do? The commutator rings ensures to reverse the direction of the current every 180 degrees. For example, here the current is going down. When the coil rotates and this part reaches the other side, the current needs to be going up or in this direction. If you go back to the video, you would realize that the current here is going towards, but when it rotates, here it goes away. So
direction throughout the motion, so the coil will continue rotating.
See, the current flips. The current is going towards, when it reaches the other side, it flips. So the commutator changes the polarity every half turn. Alright, so it keeps flipping or reversing the direction of the current. Why does the commutator changes the direction of the current? To keep the coil rotating, to maintain the same direction of the forces. This is the function of the split ring commutator. Now this table shows the purpose of each part of the electric motor. Please take a picture of this. It's very important. It shows you what is the function of the coil, what is the function of the magnets, what does the carbon brushes do, and what does the split ring commutator does. All right? All right. Were you able to take a picture of the table? All of you? Okay, you took a picture. That's great. What about the rest of you? Did you take a picture of the table? All right, good. Good. Okay, you can write it down later in your notes. But most importantly, it shows what a split ring commutator does, because this is an important question. If you're asked about the split ring commutator and about its function, it has two functions. One, to avoid writing all of this in what? Hold on. Yes, Dana.
Mister, can you go back to the table? Because I was fixing my Wi-Fi.
All right, this is the table. Can you see it?
Okay, thank you.
All right, good. All right, if you're asked a question about what is the function of a split ring commutator, it has two functions, okay? One, it rotates with the coil. Two, it reverses the direction of the current every 180 degrees, every half a turn, to keep the coil rotating. Okay? Now, if we want to increase the rotation of an electric motor, how can we do that? If we want to increase the force of rotation, if we want it to rotate faster, who can tell me how can I make an electric motor rotate faster? What are the things that I can change to make it rotate faster? Come on, if you have an answer, please let me know. How can I make it rotate faster? Yes, Dana, you have an answer. Nobody has an answer. How can I increase the force? We talked about that in a bit. How can we increase the force acting on the wire? We can increase the force acting on the wire by using a stronger magnet. Okay, here. Using a stronger magnet, increasing the number of turns, or increasing the current. These are the three things that causes the electric motor to rotate faster with a greater force. Increase the strength of the magnets, increase the number of turns of the wire. So instead of one wire, you can increase the coils. More turns of the wire increases the force, and more current increases the force. All right? Okay. Okay. So basically, let's see. Which of the following would cause a DC motor to spin more slowly?